In this question, the position vector of an ice skater is given. All distances are in meters, and we are supposed to find the velocity vector. So let's revise the concept. Velocity using position is found by differentiation. So velocity is given by the derivative of r with respect to time, where r is the position vector. So in this case, the position vector is given in the column notation. X coordinate is on the top and the y coordinate is on the bottom. Hence, we can say that to find the velocity's x component, you have to differentiate the x component with respect to time. So in this case, that x component, as we can see, is this. Let's write it down. A e to the power bt into cos t. So if you differentiate this, we'll get the x component of velocity. Similarly, for the y component of the velocity, we'll do dy by dt. And the y component is at the bottom. So to get the answer, the final velocity vector at time t, let's differentiate x and y with respect to time. Dx by dt will be equal to d by dt of a e to the power bt into cos t. So now, as you can see, there are two functions of time. So we'll have to use the product rule. According to the product rule, let's write down the logic. Let's say if you have to differentiate a into b with respect to x. So it's the product. So the rule goes like this. A into db by dx, which is the first function into the derivative of the second function plus the second function into the derivative of the first function. In this particular case, a is a constant that will be taken out of the integral. E to the power bt is the first function and cos t is your second function. So let's differentiate. A we will write as it is. First function is e to the power bt multiplied by the derivative of the second function, which is cos t. Derivative of cos t is minus sin t, plus the second function is cos t multiplied by the derivative of e to the power bt. Now the derivative of e to the power bt will be e to the power bt multiplied by b using the chain rule. So we'll write e to the power bt into b. And that's the x component of the velocity vector. Find the y component. Let's differentiate the y with respect to time. Vy equals to dy by dt. The y component, as we can see, is this on the top. So we'll write d by dt of a e to the power bt into sin t. Like in the previous case, a is a constant. We will take that out of the derivative and let's use the product rule to differentiate. A first function here is e to the power bt multiplied by the derivative of sin t is cos t, plus the second function in this case is sin t multiplied by the derivative of e to the power bt, which will be e to the power bt multiplied by b. And that is the y component of the velocity. And now if we write the velocity vector in the combined form, we will get the answer as this. This is the velocity vector in which we can see the two components are given in the column vector notation. Moving ahead to the part B, where we are supposed to find the magnitude of the velocity. So let's write on the part B. How do we find the magnitude of any vector? Let's revise. If R is any general vector, it is AI plus BJ. So the magnitude is given by the Pythagoras theorem, square root of A square plus B square. So let's apply the same logic here. We'll write magnitude of velocity will be given by square root of the x component is mentioned over here. Let's write that down. A b e to the power bt cos t minus a e to the power bt sin t. This is only the x component. So we square that and we add the square of the y component, which will be this, plus a e to the power bt into cos t squared. Be careful that the square root which we have drawn has to be across the entire expression. Now, in the exam scenario, we don't want to waste our time just drawing a big straight line for the square root. So to avoid that, we'll use a trick. Square both sides of this equation. So we'll get magnitude of v squared equals to, then the square root on the right-hand side will vanish, which will make it a little easier to handle in an exam scenario. So let's use the a minus b whole squared formula for the left expression. And for this expression, we'll use a plus b whole squared. So let's solve. a square b square e to the power bt. Now the square of e to the power bt will be e to the power 2bt. In any case, I'll write it on the top right. E to the power bt squared is written as e to the power 2bt cos square t plus b square, which in this case is a square e to the power 2bt sine square t minus 2ab. Now we'll have to multiply the two terms together. Minus 2, and then on multiplication we'll get a square b e to the power 2bt, and then we have cos t sine t. So this is the expansion of the left term. Now we expand the right side. So to get that, that's the formula of a plus b whole square on the right hand side. So we'll get a square b square e to the power 2bt sine square t plus a square e to the power 2bt cos square t plus 2a square b e to the power 2bt into sin t cos t. Now, if you observe, two terms are going to get cancelled out. So look at this term. This is exactly the same as the below term, and we have a plus and a minus. So the last two terms will get cancelled out. The terms which are left are these four. Now let's simplify this. So observe in this term on the top and this one on the bottom, terms are common. So a square b square e to the power 2bt is common. We can take that out of the brackets. So let's write that down. A square b square e to the power 2bt, and in the bracket we'll write cos square t plus sine square t, which is equal to 1. Remember, sine square theta plus cos square theta is 1. In the second term, in the second term and the fourth term, again, let's take out the things which are common. So we'll get a square e to the power 2bt into sine square t plus cos square t. Now the two brackets will be equal to 1, and eventually we get a square b square e to the power 2bt plus a square e to the power 2bt. In this case, let's take a square e to the power 2bt as common. We'll get b square plus 1. That's the square of the magnitude. Now, in order to find the magnitude itself, let's take the square root now, because that is important. So we will get just square root, we'll get a into e to the power bt square root of b square plus 1. So let's just cross check. In the part B, they have mentioned a into the power ebt square root of 1 plus bt square, and that's the answer for part B. Moving to the part C, they have given some additional information. At time t is equal to 0, the displacement of this ice skater is given and the velocity is given. Let's bring in the equation of the velocity vector, which we had found earlier in part A. Since they have given the velocity is given by minus 3.5 and 5. So let's equate the x component of the velocity vector with minus 3.5 and the y component of the velocity vector with 5. So let's write it down. Velocity x component at t is equal to 0. So we'll put t is equal to 0 in the x component. So we will get a, b. Now e to the power of 0 is equal to 1. And cos 0 is also 1. So we'll get ab minus sine 0 is 0. So a into b is the x component, which in this case is minus 3.5 as they have given. Velocity y component at t is equal to 0 will be, you have a sine t in front, so the entire expression will be 0 plus a, and that is equal to 5, which means a directly can be represented by 5. And to get the value of b, we use the x component. So we will write b is equal to minus 3.5 divided by a minus 3.5 divided by 5, which comes out as minus 0.7. Hence, the value of b is minus 0.7. And that's the answer for part C. Moving to part D, we have to find the magnitude of the velocity when time t is equal to 0. So in the part B, we already had found out the magnitude of velocity vector. Let's write that down. This is the magnitude of the velocity. We have to find the magnitude when the time t is equal to 2. So let's put the value of time as 2. So we will get a into e to the power 2b square root of 1 plus b square. Let's simplify this expression by putting the values of a and b. A is 5, e to the power of 2 into minus 0.7 square root of 1 plus minus 0.7 squared. And if we simplify this using the calculator, we'll get 1.51 as the answer. And that's the magnitude of the velocity vector when time t is equal to 2. Moving to the part E, at a point P, the ice skater is skating parallel to the y-axis. We need to find the distance OP. So we will use the logic that whenever a line is parallel to the y-axis, its x component is always a constant. Let's repeat, whenever a line is parallel to the y-axis, the x components are always constant. Since the ice skater is moving parallel to the y-axis, so the x component is constant. This does not mean that the x component of velocity is constant. So if the position vector, let's say, is ai plus bj, if the skater is moving parallel to the y-axis, that means the x component, which in this case is a, has to be a constant. In other words, we write down the position vector x component has to be a constant. Now, since the x component of position vector is a constant, how do we get the velocity vector? So velocity x component, as we know the rule, we differentiate the r with respect to time. Now, since the r itself is a constant and we know derivative of a constant is 0. So the x component of velocity is equal to 0. Now, earlier we had found out the velocity vector equation in the x and y form, which is this. We have to equate the x component of the velocity to 0. So let's write it down. We'll get a b e to the power bt cos t minus a e bt sin t. So this entire expression will be equal to 0. So if we simplify this and take the second term on the right hand side of the equality, we'll get a b e to the power bt cos t equals to a e bt into sin t. Let's see which terms can get cancelled out. So a on both sides will get cancelled out. In this expression, we can also cancel out the e to the power bt. As we know, e to the power bt is always greater than 0. So we can cancel that out. Eventually, we get b cos t equals to sin t. And on simplifying this, we'll get tan t is equal to b. And the value of b, which we had found, was minus 0.7. And to simplify this, we'll use the tan inverse function, tan inverse of minus 0.7. Solving this, we'll get t as 2.53. Let's use that to get the position vector itself. So the position vector is this. T is equal to 2.53. So the value of x coordinate will be a into the power e into b into 2.53 cos of 2.53. So this will give us the x component of the position vector. And if you solve this, we will get x as minus 0.697. For the y component, we'll do a into e to the power bt into sin t. So b multiplied by t is 2.53 multiplied by sine of 2.53. And if we again put the values of a and b, which we had found earlier, eventually we will get y as 0.488. Let's write down the position vector now. So we'll get OP vector will be equal to minus 0.697i plus 0.488 j cap. Let's go back to the question to find out what we were supposed to find. We were supposed to find the length OP, which is nothing but the magnitude of this vector. So to find the magnitude, we again use the Pythagoras theorem. So we'll get 0.697 squared plus 0.488 squared. And if you simplify this, we will get the answer as 0.85 meters. And that's how we solve this question.